Right. Well, welcome everyone to the Halloween installment of the NAG-ROMS seminar. It's a great pleasure today to introduce Professor Nan Chen from the Department of Mathematics, the University of Wisconsin, Madison. And so he will be talking about stochastic and statistical reduced order models. It's a great pleasure. We're talking before the seminar, so so the organizers are making an effort to include different views, not necessarily the old the classical type of approaches, which is what we're doing, but also like different points of view for reduced order modeling. And this is it's a great pleasure to have Nan talk today about statistical and stochastic type of models, which is something that's not usually discussed so much in the community. So I think well, I'm looking forward to it. And with this, I'll let Nan give his talk. Thank you, Nan.
Thank you very much, Trent. Thanks for the invitation and thanks for the introduction. So today I will share some of my thoughts about stochastic and statistical reduced models. Part of this talk will be like educational purpose, but later I will also include some research results. So hopefully everyone can take some message from this talk. I will try to divide my talk into different parts. So I'll first give a quick overview about what are the stochastic reducer models and why they are needed. Then I'll focus on part 2 and part 3, which are developing simple but useful stochastic reducer models and stochastic reducer models with analytically solvable conditional statistics. So I'll briefly mention about statistical reducer models. It is related to the stochastic version, but it has different purposes. And I will spend like 2 minutes at the end to discuss this thinking in the reverse way, how these reducer models can help develop more sophisticated physical models. Okay, so let's start here. So perhaps this is the first time you've heard about these stochastic reducer models. So stochastic reducer models, they are different from the traditional determinist models because the stochastic reducer models will include additional stochastic terms. And these terms will be important for at least 3 purposes. The first one is they try to describe the statistics of these small scale or unresolved scale features when we consider multi-scale systems. So you can think we no longer need these small scale equations. So stochastic reducer models can help us to reduce the dimension of the systems. And second, these stochastic terms can also be used to compensate the role of the combined effect of many of these complicated nonlinear terms. So effectively, after you do dialoging or other method, you will end up with a lot of these nonlinear terms, right? So each time you have to do the multiplication, you also need to add all these terms together. But if in some situations, you can ignore these terms, but you try to add a stochastic part, so your calculation or your computation cost can be greatly reduced. So in this sense, we are not aiming at reduce the dimension, but we are aiming at reduce the complexity of each equation. Of course, 1 and 2 should be combined together. And also, these additional stochastic terms will help us to allow the development of the so-called moment equations to approximate the time evolution of the full statistics. And this is another viewpoint of reducer models. So it tries to reduce the complexity in the statistical viewpoint. So it's not just reduce dimension, but you can think if you want to fully represent the PDFs, the probability density function, but that's too difficult, we can instead just capture the mean variance or the first few leading moments. So it's another way of reduce the complexity or reduce the systems. So that's why we need these stochastic reducer models, because it can provide different ways to help us to make things simple but useful. So if you still have no idea about what these stochastic terms they look like, you can simply think these are kind of some closures, but they are like a stochastic closures, right? one thing I do want to mention is that these stochastic models, by design, and they do not focus on reducing the pathwise error in a single long trajectory. I think this is easy to understand because you put the stochasticity, which is, impossible to predict in a pathwise way. So our goal is not to just try to make sure this reduced model has a very nice capturing of the long-term trajectory. But our goal is we try to make use of these stochastic terms to improve the skill of reproducing the crucial statistical features of the system. So maybe we don't care about each single trajectory, but we do care if we run these stochastic models multiple times, then the ensemble or the statistics of these stochastic reducer models should capture the statistics of the full model. So that will have a lot of applications, especially when we have uncertainties. So on the other hand, if we have appropriate stochastic reducer models, they will also help significantly to capture the underlying physics. So just don't think just these stochastic terms only helps you to improve the variability of your variable, but if you design them in a very suitable way, you can understand the physics very cheaply with these stochastic terms. So I list a few applications or key points when these stochastic reduced models are useful, especially for chaotic or turbulent systems. They can help us to understand the fundamental physics, especially multi-scale features. They will be very useful for the statistical or ensemble forecast in a cheap way. They are extremely useful for data simulation, uncertainty quantification, and they can also be used to study the sensitivity analysis or the statistical response if you have a turbulent system. And they will also be useful for the optimal control, and especially this optimal statistical control when you try to control the moments. And they can also be helpful for prime transformation, state transformation, and even if you have a good model, you can use the model to generate a long trajectory. So you can train your neural network, and then you use the short observation data for the transfer learning. So there are tons of applications of these stochastic reducer models. So now I try to discuss some concrete examples. So you don't need to have any backgrounds about these stochastic models, but I try to go through things from very simple case to a more complicated things. The first thing is I want to discuss this Ornstein-Uhlenbeck process, which is our building block for the reducer model. Then I'll go to more complicated situations. So what is this Ornstein-Uhlenbeck process or U process? So it is one of the simplest possible stochastic equations, and it is just like one scalar equation. Here xt is a state variable, and this a is a constant, f is a force in which can depend on time. It can also be a constant. So without this last term, this is just a simple ODE. It's a damped force system, right? But now we have this additional stochastic term. Sigma is a constant. This dw dot is a white noise. So w satisfy like a Gaussian process, a Gaussian random variable here. So I do want to mention that we use stochastic models in both mathematics and physics, but mathematicians and physical scientists, they try to use different notations. But essentially they're the same. You can think you divide by dt over the left and right hand side. So you go from the first equation to the second equation, but just a slight different notation. And as I mentioned, this Wt is a stochastic process, and it is a real valued. And it has a name called the Wiener process, or sometimes it's also called Brownian motion. Its feature is it has independent increment with a Gaussian distribution. So think you initially at time s, now you're at time t. This Wt minus Ws satisfies Gaussian distribution with mean 0, and its variance depends on this time gap. Right? You can think if you have only a small movement forward in time, then this noise should be small. But if you want to forecast for a long time, then this noise will be more significant. But all you need to do is to have this Gaussian distribution. So when you try to compute this stochastic equation, first you can define this G as this deterministic part, or we call that drift term. Then the exact solution of this equation will be, if you think about the standard integration, so the next time instant equals the value at the current time instant plus the integration of the deterministic part plus the time integration of the stochastic part, right? So without the last term, again, this is a standard calculus you have learned. So to understand this equation, let's just think about the numerical discretization using the analog of the Euler method, which is called Euler-Maruyama. So effectively, if you move forward by delta t is tn plus 1 minus tn. So your xn plus 1 equals xn plus gxn times delta t. This is deterministic part, right? But also you need to add the increment for your stochastic part. So the stochastic part is this constant, which is a noise amplitude or noise coefficient times this delta Wn. So what is this delta Wn? So delta Wn is the increment due to the noise, and you multiply by the square root of delta t because it's a standard deviation. If it's variance, it's delta t. So it's square root of delta t times the random noise. And this random noise is a standard Gaussian distribution with mean 0 and variance 1. And if you put this delta t inside this random noise, then essentially it's Gaussian white noise with 0 mean and variance delta t, right? But now you split them. So effectively, this increment is still a function of this delta t. But all you can see is we solve all the deterministic part, then we add a noise, which is driven by this Gaussian white noise or Gaussian white number. So that's it. And you can expect, because this is random, so each time when you run a different realization, your value can be very different. So usually we care about the statistics because each single trajectory can hard to be predicted, but the statistics is usually more robust. So that's the building block of developing stochastic reducible models. I want to move forward to a slightly more complicated system. So it is still called the OU process, but it's complex value. So the difference is that now in addition to a constant here, I also put this I, which is an imaginary unit times this omega. So in such a way, this U will be a complex number. And F can also be complex. So this W now becomes a complex white noise, which is a real white noise plus I times another real white noise over square root of 2. Over square root of 2 to make sure this is variance of this party equal to 1. But this is essentially similar to previous case, but just I try to introduce this, we call that phase term. Usually it is a term to describe the oscillations of the system. Right, so without noise, you can think this is gamma is a damping, this omega is a phase, this F is a forcing. So that's all what I want to discuss for the simplest possible stochastic process. And maybe you think this is way too simple and how this is connected with the reducible models. Now I'll tell you how this simple OU process will be helpful to develop useful stochastic reducible models. Oops. Okay. So now I will discuss this key step towards using the stochastic reducer models to characterize complicated nonlinear PD. So let's just think about a PD in fluid and geophysics. So also for simplicity, let's consider this PD with only one spatial variable x. So the state variable will be this u, depending on this one-dimensional x and time t, right? So many of you are familiar with the features of these fluids or geophysics. You know these PDEs usually have quadratic nonlinearities, and these quadratic nonlinearities usually comes from advection, right? So in many cases, you have good boundary conditions, say periodical boundary conditions. So you can apply a spectrum decomposition using Fourier modes. Then we use this U hat K to denote the time series of the spectral mode associated with each wave number K. And just by standard calculation from the spectral method, you can write down the equation of this U hat K. which will have this damping that comes from the damping in the PDE or the dissipation from PDE, the Laplacian term, right? And you have this I omega k, which comes from the dispersion relationship, the linear dispersion relationship, and you have some forcing, but you will also have this term, and this will be a summation for all these wave numbers, and it includes this quadratic nonlinearity. And this term corresponds to the original quadratic nonlinearity due to advection and other features. Of course, you can solve this equation, so that's a standard spectral method. But this part, it contains a lot of terms. It contains all these summations, and also have to take the multiplication. And the most expensive part of this equation will be this nonlinear part, right? So now let's try to revise this equation. We keep everything for the linear part, the damping, the phase term, the forcing term. But what if we replace this complicated nonlinearity by a single stochastic term, right? So you can expect these two equations, if you run for a long time, they will be very different, right? Actually, because this is random, so it will be different from any equations. But what will this equation benefit us if we replace this entire complicated nonlinearity by this simple noise? So you can guess, we reduce the computation cost, right? But what else we will have? So before I show you the numerics, I will tell you something here. Usually, many nonlinear terms in the original equation involve high frequencies, especially if this m is much bigger than this k. So the time series constructed by these terms can be fully chaotic and has very short temporal correlation or has very short memories. So this is a very good motivation to tell us, because this nonlinearity will just most likely trigger you something with very fast oscillations with very short memories. So it provides us a justification to replace these complicated nonlinear terms with some effective terms and the effective stochastic noise. Maybe you need to modify this damping as well. So if we replace these terms by stochastic noise, then you can think, although each trajectory will be different, the overall statistics can still be similar. So the goal of the stochastic reducer model is to capture the overall statistics of the original model. And if you are familiar with this so-called stochastic model reduction developed by Maida Timofeyev and Eric Van Danden 22 years ago, you know that the equation of the motion for these small scale or unresolved fast modes are usually modified by representing the nonlinear self-interaction terms between the unresolved modes by damping the stochastic terms. So they studied how this stochastic noise can effectively represent the statistical feature of these complicated nonlinear terms. So that's very nice. So if you believe this term, the combination of these terms is like fast waves or high frequency or short memory, then it makes a lot of sense to simply replace all these details by a single and simple stochastic term. So when you try to handle the stochastic equation, you notice that you have only 4 parameters: this damping term, this phase term, and this is a constant forcing and the stochastic noise. And the very nice thing is, for this OU process, the statistics is Gaussian distribution. So you can use the 4 statistics to determine these 4 parameters in a unique way and in a very simple way. You have analytical formula. And these 4 statistics will be the mean, the variance, and the deconvolution time. And the deconvolution time has like 2 parts, the real and the imaginary part. So you basically have 4 statistics. So if you can get a time series from your original model, then all these coefficients can be determined uniquely in a very simple fashion. So that's a good thing about this model. So now let me show you a quick example. I call that a simple example, but it's not that simple. So let's say we consider this 2-layer quantity-geometry equation, and if you're not familiar with this equation, just think it's a like PD set of PDEs. This kind of PDE is usually widely used to describe a turbulent field in atmosphere and ocean science. So because it's PD, so when we try to solve it, we have to think about the spatial discretization. And here I use the spatial resolution of 128 times 128 in a two-dimensional space. And it has these two layers. So in total, you will have more than 30,000 of the mode. And if you want to run this model, it is pretty expensive for mathematicians, although it's a very simple model for climate scientists. So it will take like 20 minutes for a single run. But usually when we use these models, we try to use them for data assimilation and other purposes. So have to run this model many, many times. Then you will take a lot of time to finish these ensembles. So now we try to see if we can use this complex oil process to mimic the feature of this upper layer flow field of this QG model. So essentially, we run this model once to generate a time series of this upper layer. Then we use four statistics for each Fourier mode to determine the coefficient of each oil process. Then let's see what we can get. So this is what we get. In this panel A, we show this the truth at one specific time instant. It's a snapshot. The truth is this two-layer QG model, and I only show the up layer feature. And this is the truth after we do a truncation. The truncation is done by keeping the modes up to k equals 11. And this is because when we look at the spectrum, after k equals 11, the energy is pretty small. So you can see after we do the truncation, we can still keep most of the features. But when you solve the PDE, you have to really resolve 128 times 128 because otherwise your solver can be quite unstable. So now we replace each of the Fourier modes, which will look like here, by this stochastic equation. And I show in panel E and F the time series of the original equation and the time series of this oil process. So because both of them are just two free runs, so you do not expect point-wise they match each other. But you can see the overall behavior of these two time series, they look pretty similar. And you can actually derive the statistics from this time series, and the statistics match each other very well because we calibrate this oil process by matching the statistics. So now look at this panel D. So panel D is a simulation, a snapshot using this set of the oil processes. And it has all these nice features with these eddies or vortices. So again, we do not expect point-wise match because they are two free runs. But overall, if I ask you which of these two figures is from the QG model and which is from the linear stochastic model, the oil process, it's hard to tell, right? Because statistically, they look very similar. But one thing I really want to highlight is that for this panel D, I only keep 200 modes. And each of these 200 modes are just these simple stochastic equations. So if you use 200 modes for the deterministic model, you still need to spend a lot of calculations here. But now I just use a constant times Gaussian noise. So it's much cheaper. And comparing with the original 30,000 modes to solve a QG model, I only use 200. So computational wise, it's much cheaper. Just you spend like 3-5 seconds to get all these simulations, compared with like 20-30 minutes using the original model. So actually, we use these types of the stochastic model to forecast the statistics. Then we use these statistics to do data assimilation when we try to handle the real observational data of the Arctic sea ice, and we try to recover the ocean field using this kind of model. So that makes this practical calculation really possible. Otherwise, you have to run your QG model like at least 50 times. But each time it's like 30 minutes. You need 1 day to wait for one run, but you need to run this many, many times. So now you may have some feelings, right? How we can use these stochastic models. So we can start with PDE, one PDE, then we can try to get a time series from PDE. We match the statistics between the reduced order model, stochastic model with the PDE to get the coefficients. And we model each of the Fourier mode using the stochastic model. So that's a baseline. Now, if we want to consider more complicated situation, how we do that? So I want to introduce this general philosophy. So let's try to go one step further. So what if we have a PDE system, meaning that we have more than one PDE? So of course, you can say we model each PDE equation by one stochastic model. But the thing is, different PDE components, like the velocity field in horizontal direction and vertical direction, they are coupled. So what we can do is, I try to show the idea using the linearized shallow water equation, and we can consider the two-dimensional domain with periodic boundary condition. So just think about this PDE. You have a two-dimensional velocity field. You have a height. So this height is a shallow water height. So essentially, you have three-dimensional system, right? And this epsilon is the Rossby number, which is the ratio between the growth and the advection. So what we do is we can put all these three variables into a vector, and you write down the previous equation into this vector form. And what you do is you try to assume a plane wave ansatz as like, again, it's kind of the Fourier method, and you plug this into the original equation. So what's important here is this R. So R is an eigenvector. So this exponential function is a scalar, but R is a three-dimensional vector which tries to connect the three components. So essentially, you try to write down the Fourier coefficients after you plug into here. And this Fourier coefficients is again a one-dimensional time series. Because you only need this one-dimensional time series, then you multiply by this R, which is three-dimensional vector, to connect all these three different components. So essentially for one free mode, you need one equation. But now you have these three different components. So this omega term, which is a dispersion relationship, will be important. And actually, when you plug this back to this linear equation, you can find different characteristic forms. And it will be a 3x3 matrix. You should end up with three different eigenmodes. And these three different eigenmodes have their own physical meanings due to different dispersion relationships. So what you do when you try to build a stochastic model is you get information about this dispersion relationship, then you write down these ansatz of the linear stochastic model, the Euler processes, but you plug in the exact dispersion relationship from your analysis to determine these terms if you don't want to do the data-driven method. And then you match the statistics of the damping, the force, and the noise. So you can get different equations for the stochastic component. Then eventually, the fourth solution will be given by the combination of all these three different characteristics. But each of them will satisfy this Euler process. So this is where you try to deal with high-dimensional PDs. So we try to do a linear analysis. You try to get a dispersion relationship for each eigenmode. Then you use that to help you build your phase term here. So at least your stochastic term will have the right oscillation frequency. Then you determine the other coefficients by the data-driven methods. So of course, Euler process is the simplest possible equation, and it is a good way to approximate the original complicated PD if your statistics are nearly Gaussian. But in many cases, we can see time series with a lot of extreme events with strong nonlinearity. So what should we do? And what we can do is we either introduce nonlinearity or multiplicative noise, or sometimes we need both to help us. So there are, again, many ways to build stochastic models with non-Gaussian features. But what I want to discuss here is only like one equation. And again, I think this is the simplest possible way to model the nonlinear and the non-Gaussian time series. So the equation I want to use here is, again, it's a linear equation. But instead of using a constant as noise coefficient, now we can use a function of the state variable as a noise coefficient. And it has a name, it is called the multiplicative noise. If it's a constant, then it is called the additive noise. So despite the linearity here, this multiplicative noise will help us get the non-Gaussian statistics of this U. And the nice thing about this kind of equation is, despite this non-Gaussianity, the coefficient of this sigma u can be determined using an analytical formula. And this analytical formula can be obtained by solving the Fokker-Planck equation. And you take the integration twice, you can get it. So if you are interested, you can look at this paper. One simple example is in many cases, like in climate, we always like this gamma distribution, which means you have a skew distribution with a really long tail. And if you prescribe this distribution of the U to be a gamma distribution, then you can derive this noise in a very nice way, and it looks very simple. So previously we did some work using this equation to model the convective activities for the clouds and for the Madden-Julia oscillation. And if you're interested, you can look at this paper. So what I really want to show you as a simple illustration is that now I use this complicated nonlinear OSD with correlated additive and multiplicative noise to generate a true signal, which is shown in the blue curve here. And I consider two different regimes. And for this time series, the blue one, you can see the time series is highly non-Gaussian with a lot of these extreme events. And for this one, you can see roughly we have this going back and forth. So the distribution is a bimodal distribution. And in both cases, the distribution not Gaussian. The Gaussian is black. You can see the blue curve is very far from this black curve, right? So usually in nature or in many applications, you don't know the underlying dynamics, but you will just get this time series, the blue curve. So you want to find a simple way to model this blue curve, right? So since we have no idea about what the underlying dynamics is, we can always start with this linear model with multiplicative noise. Then we use the previous slides, the method describing there, to determine these noise coefficients. And this red curve is a simulation from this linear model with multiplicative noise. So you can see that despite that this equation is much simpler than the truth, it can mimic a lot of nice features of the truth, like these highly non-Gaussian PDFs. The autocorrelations are also very similar. And now you can see that this sigma u noise coefficient is not a constant, because if it's a constant, you'll get a Gaussian distribution. So it really depends on the state variable, this u, right? So like in the middle of this u, around 2, you have strong noise, so you can trigger extreme events. But if you are already at a large value, you cannot have a large noise. You basically will be damped back to your mean state. I compute this numerically based on this analytical formula. I just divided this entire interval using different bins. But this still helps you to get a nice profile. You can see how it looks like here. So the last simple stochastic parameterized equation I want to describe is this so-called stochastic parameterized extended gamma filter model. So this is another way to describe non-Gaussian features. So previously, we just used a linear equation with multiplicative noise. But now you can start from your OU process, like the first equation. If you think this gamma, omega, and B is 0, if you think gamma, omega, F, and sigma k are all constants, then this is the OU process, right? We described just now. And if it's an OU process, then the time series will have a Gaussian distribution. But now we can do something slightly fancier. We can say, hey, let's make this gamma, omega, and this B to be a stochastic process instead of just a constant. And for each of these three variables, we use a simple OU process to describe their time evolution. So overall, if you think about this four-dimensional system, that becomes a nonlinear equation, right? Because gamma now will multiply by this u, and similarly, omega will be multiplied by this u. So overall, it's a nonlinear, so you are able to trigger nonlinear, non-Gaussian features. So what I show here is this u is the simulation from the first equation, and you can see a lot of irregularity in the oscillations and a lot of these extreme events. And in fact, if you think this gamma as a time series, so if gamma is positive, then this term is damping. So it is mostly like a stable phase. But if this gamma at some time instant, it becomes negative, then this minus gamma will become positive. So that will trigger this exponential increase within a short window, and you can see extreme events. And similarly, when this omega has different values, you will have slow or fast oscillations. So really, this system is like a quadratic nonlinear system, but all these three, like we call that latent variables, they are linear equations with Gaussian statistics. But once they interact with this U, you can trigger nonlinear features of this U. And this kind of model is a very useful cheap forecast model for data simulation or filtering. And previously, Michael Branicki has done some very nice work for the Navier-Stokes equation. And my postdoc Chang-Ho Mo did some also very nice work when he combined this machine learning with this kind of model to do data simulation. Okay. So so far we just consider very simple one-dimensional or these four-dimensional stochastic models. And basically we focus on using these models to model each of the Fourier modes. Then we run these different Fourier modes independently to build reduced order models. And these models can be useful to predict the statistics or data simulation. So now I want to slightly change the topic. Let's say we try to build really a high dimensional, a relatively large dimension of the reducer models, but we want to make sure these reducer models have some solvable conditional statistics, which means they will have some nice features to help us to move on to other topics. Again, let's consider this general formula of turbulent systems. And again, we consider many equations in fluids or geophysics. So U is a state variable. It's a multidimensional state variable. This L and D are the damping term and the phase term. So L is negative definite, and the D is skew symmetric. This F is a forcing term, and this sigma U W dot will be some noise. With or without them don't matter too much for now. And this BUU is a quadratic nonlinearity. Again, it can describe advection or other nonlinear features. So let's think about a decomposition of this U. We put X and Y as two vectors, which will combine to represent this U. So think X is in a relatively low dimensional space, which is a collection of large scale modes, and Y is the remaining relatively high dimensional superspace. You can think about a smaller scale or unresolved scale modes. So for this BUU, actually, you will have three terms after you do this decomposition. You'll have BXX, BXY, and BYY, right? So BXX will be the largest scale interaction. BXY will be large and small scale interaction. One of the interesting things is BYY term. So Y itself is relatively small scale. So BYY, the quadratic term, will usually involve high frequencies. And because it looks like this high frequency, short memory, and pretty noisy, so we can try to represent this BYY using some effective parameterization or some systematic closures to eliminate this effect. And there's some very good technical details, again, developed by Chang-Ho Mo in this paper if you're interested. So if we can approximate this BYY term, then we drop it, we use stochastic noise to replace its effect. So after that, our system will look like this equation. So we still have all these nonlinearity in X, and we can have X times Y, but now you do not see YY term, right? So the nice thing about this equation is actually there are two reasons. So we'll have some good of this kind of use, which will help us a lot when we try to do the statistical analysis and data simulation. So the first nice feature about this model is because now Y itself appears only in a linear way, but although the entire equation is highly nonlinear. So because of this conditionally linear feature of this Y, the statistics of this Y given X will be a Gaussian distribution. So the marginal distribution of Y will not be Gaussian because Y equation is nonlinear. But if X is given, then everything after X is given is a linear function of Y. So that's why the distribution of this conditional distribution is a Gaussian distribution. And what's even nicer is that this conditional mean and conditional covariance can be written down using this closed analytical formula. And usually when we do data simulation, we aim at solving the distribution of the state variable given the observation, which is exactly this equation. So that means for this kind of system, when we try to do data assimilation, we have this exact closed statistical formula. So we can avoid using numerical method based on ensembles. So we can avoid all these dirty works we have to do, like tuning the coherence, to inflate the noise, and many other things. And the second reason we try to build this system is that many well-known models will fit into this modern framework. So there are a lot of these physics-constrained nonlinear equations. If you think about different types of Lorentz models, they will belong to this framework. If you think about the Chinese-Devol flows, it will belong to this framework. And many of these reaction diffusion equations in neuroscience and ecology also belong to this framework. And more importantly, if you think about multi-scale models in turbulence, like Boston's equation or Shutter-Watt equations, if we treat them suitably, they will also belong to this framework. So really, this framework can provide us this useful tool to do data assimilation and to do the statistical forecast. So that's why we make use of this fast wave approximation to eliminate the system, but include some stochasticity to describe its effect. I list all these important applications. At the very beginning, we use this kind of stochastic models to develop low-order representation of this very intermittent time series. You can see, right? There's a lot of extreme events. We use like two variables to describe these two time series, but we realize that these two variables themselves may not be sufficient. So we add another two hidden variables to describe this large amplitude and irregularity in the phase. But this equation belongs to that framework. So we use this equation to do data assimilation to recover the latent variable and do the forecast for this monsoon. And we also use this kind of model to build reducer models for CIs with discrete element method. And because of this solvable analytical feature, this system actually allows us to solve this high-dimensional Fokker-Planck equation, which is a very useful tool to do the forecast. This kind of system also allows us to build coupled tracer and flow model for data assimilation. And recently, we are doing some work using this kind of tool to do this physics-informed data-driven sparse model identification. So one really interesting feature is when you try to reduce the model complexity, you may think we just drop the terms with small coefficients. But actually, that's not true. So you need to drop the terms with the weakest causal contribution to the dynamics. So in this paper, we use this causality-based method to do the sparse identification. So now I want to move to how this model can help us to solve some real-world problems. I just show one simple example, which is this Lagrange data assimilation. And you know this famous figure, right? So there was a boat which had an accident here, then it contains all these yellow ducks. These yellow ducks was released after this accident. Then after a few years, people see yellow ducks were everywhere and realize these yellow ducks, they play as a role of the tracers like this. So if you can observe the trajectory of these tracers, then you can recover the ocean field, right? So usually you try to have a model, your ocean model, and you try to combine a model with observations to reduce the uncertainty or try to improve the accuracy to recover the ocean field. Because if you only have the model is turbulent. For a long run, your uncertainty will large. But after a long run, if you have observations, some observations will be some constraints, so you can reduce the uncertainty. So that's the idea. Previously we did some work using this kind of framework to show the information barrier and to design some cheap practical strategies to recover the multi-scale features. So if you're interested, you can look at these papers. But I only want to show the framework here and tell you why this reduced order model can describe this kind of data assimilation problem. So let's just consider a two-dimensional domain, 0 to 2 pi square. And the velocity field can be written as a Fourier summation. And this is a Fourier coefficients, basis, and eigenvectors. And now we use the previously developed this OU process to describe each of the Fourier coefficients here, right? And for the observation is very simple. It's just a trajectory of the tracers. So you use Newton's law, dx over dt equals v plus some noise. So the most tricky part is this v, after you replace it by this Fourier summation, you found that this x will appear in the exponential function. So that means the tracer equation is always a highly nonlinear equation, right? And so when you couple the observation equation with underlying dynamics, your total system will be nonlinear because of this nonlinearity. But if you are given this x, then what you want to recover is this v hat k, that's the coefficients of the ocean. So if you know the coefficients, you will know the ocean. So if you condition on this xl, or if xl is given, then the equation of this v hat k will be linear. So it is a conditional linear system. So it belongs to the framework we just developed. So we can use the analytical formula to recover this u condition on this x or this distribution. So that really helps a lot for data simulation because this nonlinearity can cause many different issues. But now we can avoid that by solving this entire system using analytical formula. So in my last maybe 10 minutes, I will discuss this statistical reducible model. So statistical reduced model can be regarded as reduced order representation of the Fokker-Planck equation or the entire probability density function. And there are different ways to build reducible models in the statistical sense. So you can, of course, write down the moment equations, then you build closure directly. It works in many cases, and it's the simplest possible method. You can also approximate the original model to a certain family of nonlinear equations with desirable structures, like the conditional linear system I just showed. Then you can solve the moment equations or even Fokker-Planck equations much easier using the analytical properties. And the third method, which is more advanced, you try to use some physical properties to simplify the moment equations. And I'll show one page of slides about the tracer case. Actually, we can make use of our knowledge to reduce the covariance to a diagonal matrix, which will help a lot to solve the high-dimensional systems. So an efficient statistical reduced model is extremely important for carrying out statistical forecasts, and it will avoid running repeatedly the original underlying system using Monte Carlo simulations. So really, Monte Carlo simulations will be the last choice unless you have no good stochastic or statistical models for your ensemble forecast. So I show some closure method, but I show the simplest possible way to build a closure for statistical reducer models. So again, we want to use this simple example as an illustration. So it's a nonlinear system with correlated additive and multiplicative noise. It can generate all these kind of non-Gaussian features. So we do have an analytical formula for the equilibrium distribution or the equilibrium solution of Fokker-Planck equation. So you can set the left-hand side equals 0. You can take the integration, you can solve it for this system. But for many other nonlinear systems, you don't even have a solution for the equilibrium. But what I want to point out is, even though for this system, we have this very nice feature, so we can get the equilibrium solution of the distribution, still, we have no analytical formula for the time evolution of the statistics. PDF is the probability density function. But in many cases, we really care about the time evolution or the transient features. So what we can do is we can use Reynolds decomposition, and we can take the average of the first equation. So all this noise will be killed. So we get one equation for the mean here. And you can see the mean depends on the mean, but also the second order and the third order moments because of these nonlinear terms, right? So you can also write down the moment equation for the second moment. Then you have to use Ito's formula, but you will end up with something which is nice based on the mean, the second order moments, but something also bad based on the third order and fourth order moments. So then you can do the same thing for the third and fourth order moments, but in the case, your low order moment will depend on the high order moments because of this nonlinearity. So you really need to find a closure to replace these high order terms by the low order terms. right? So this is similar to the deterministic reducer model. And in fact, despite the stochasticity in the original equation, your moment equations will always be deterministic. So you can apply all these tricks. But when you apply these tricks, you need to think a little bit careful because these statistics may have some special features that the variance cannot be negative, right? So in the community, there's one commonly used method, which is called the quanti-Gaussian closure method. That is, you ignore these third order terms because if you assume everything is nearly Gaussian, so it should be symmetric. And the fourth order term can be replaced as a function of the third order term using the relationship from the Gaussian distributions. So after we do this quanti-Gaussian closure, you can see in some regions it behaves really well, but of course in some regions it doesn't do very well, especially like this bimodal region. You have two peaks, right? But if you want to use a Gaussian approximation, it will be really bad. But if you are in a nearly Gaussian region, sure, you will do very well. If you are in a highly skewed region, your mean can be pretty well, but your variance will be biased a little bit. But if you are in the fat tail region, it's similar. If your mean is perfect, your variance is slightly biased, but still they are much better than this black curve, which is bare truncation, which means you don't have a closure. Just ignore them. Think about this as an analog of your galloping truncation, right? Even in this simple case, you can see this galloping truncation works pretty bad. Here, lastly, basically, I want to show the reduced order strategy to simplify the moment equations. So again, let's think about this tracer equation. So as I said, we can write down the conditional distribution of u given x using the feature of this conditional linear system. So you will have one equation for the mean, one equation for the covariance. It's very nice to solve everything analytically. But in many cases, your ocean is really complicated. It has like 128 square modes. So this covariance matrix will be 108 to the fourth power, right? You have to multiply your number of rows and number of columns. So this equation is really a high dimensional equation. But one nice thing is, if you think now you are dealing with Fourier modes, so different Fourier modes, they are independent of each other after you replace the nonlinear terms by stochastic noise. So that gives you some very good intuition saying that, at least in the asymptotic case, this R should be a diagonal matrix. And that helps a lot because now you have n times n if you solve the entire matrix, but if you only consider diagonal component, it's just n. So you really reduce the dimension to a significant amount. So you use the mean field theorem to make this to be more formal, and you can derive the diagonal equations. And if you think you can make even further simplification, you can just consider constant for your covariance. And in data simulation, there are some other methods called 3D VAR. So in many cases, they just try to update your mean equation, but you prescribe your covariance matrix to save your computation cost. So this follows a similar argument. So my last 2 minutes will be contributed to this reverse thinking. So we always talk about we start from a high dimensional system and we use reducer models to make things simpler. But we can also think in the reverse way. If we can model some simple time series, then those simple models will also provide us some knowledge to build more complicated systems. So that's the argument here. Usually, if you want to build a model for nature, you have to use really complex systems. And very likely you have to build these complex stochastic dynamical models, SPDs. But building SPDs is really a hard topic. And no one can claim they have good intuitions to build that. So this SPD does not means you have your PDEs and you put simple white noise. You have to put a lot of multiplicative noise. You have to put a lot of parameterizations, all these kind of things. So usually there's a nice way to go from PD to SD, but not directly. So what you do is you start from your complex PD, you apply a deterministic method to build the deterministic reducer models. This is what many audience you know very well. And then based on these deterministic reducer models, we try to add stochasticity to make that to be stochastic. And this is very important because deterministic models will miss a lot of statistical features. But once you have this noise term, you can make your time series really look like nature. Then starting from here, you take the philosophy you used in your stochastic reducer models, you build your stochastic PD. So this is the entire process. And of course, you need a lot of thinking in this step. I won't show any details, but I do want to show, so we had this paper, which is the first paper we can describe its answer diversity and complexity. We call that a simple model, but simple is in the language in climate science. I can't write down the equations because it has 7 complicated PDs and a lot of add-on nonlinearity, stochastic parameterization, and multi-scale features, dependent noise. So I tried to put everything to one page, but I failed. But I really want to show you this model can capture all the simulations from nature, and a lot of these statistics is perfectly matched. So, and those GCMs will fail, but our model can work very well. But if you ask me how to build this, I cannot say I built this just from scratch. What I built was I first built a simple reducible models, and these reducible models were first developed using a deterministic method from the principal component analysis of the data. Then we add stochasticity to understand where we should add this stochasticity and where we should add nonlinearity. So using this similar philosophy, we go back to the PD, we add the nonlinearity, we add the stochasticity in a similar way, so we can build this more complicated model. So we really start from complicated PD to generate time series. We use a deterministic reducible model as a starting point. Then we think how to build stochastic terms. Then after that, we go back to the SPD, just following this line of the thinking. So that's the end. So basically, I try to introduce the stochastic reducible models and discuss why they are needed. And I showed a few simple but useful examples about stochastic reducible models and the stochastic reducible models with solvable analytical formulas and the statistical reducible models. And finally, I show very quickly what we should think from deterministic to stochastic. So many of the simple examples actually can be found in my book. So if you're interested, feel free to download it. And finally, I do want to advertise that my group has an opening for postdoc research associate. So if you're interested, please feel free to contact me. Thank you.
Very nice. Thank you, Nan, for an excellent talk. Thank you.
Thank
Really,
you.
for me, this has this was an educational experience. Seriously. So, any questions? Does anyone have any questions? Please ask. Nan. Raise your hand or just unmute yourself. Just ask the question. I see lots of people clapping their hands, but so if nobody has a question right now, maybe I can ask a quick question, and then maybe so okay, maybe Valentin, do you want to ask a question?
Hello, thank you for the nice talk.
Yeah,
very nice talk.
Thank you.
About your method to learn the nonlinear function which defines the multiplicative noise.
Yeah, I go back here.
Is it applicable to in multiple dimension and in high dimension?
Yeah. So in general, you can apply this to whatever dimension you want. But the thing is, if you really have a high dimensional system, this will become a matrix, right? So usually what we do is we have a high dimensional system. We use the deterministic method to decompose that into different equations. But we maybe try to make a diagonal matrix for this multiplicative noise. So that will be very easy if we want to determine the diagonal components. And usually, those diagonal matrix, the diagonal component will be the most important contributions. But if that's not enough, you can always use the trick I provided here, to add a few other equations together with this multiplicative noise. So indeed, in many climate applications, those time series are highly non-Gaussian. Actually, I wrote one sentence here. They consider this North Atlantic oscillation, which is highly nonlinear and non-Gaussian. So this kind of trick can be applied and you don't need to use very complicated nonlinearity if you can choose this coefficient properly.
Thank you.
Yeah. Thanks.
Nice, thank you. So Honghu, maybe?
Honghu.
Hey, Lan.
Want to ask?
Thank you. Very nice talk.
Thank you, Honghu.
Yeah, I have a couple questions, but I think we can discuss later for some of
Sure.
it. But here it's just technical ones about the Gaussian gamma distribution, the equation you wrote, which involves a square root noise,
Yes.
additive noise over there. For the equation given here, I don't quite see how you can enforce positivity on the U.
Well, if you start from a positive value, it will always be positive, because you see, if U is close to 0,
yeah,
this noise will be very small.
Mm-hmm.
So the randomness will not make it to across 0. And you have a mean state here, which is, the mean state is beta gamma plus beta, right? So U minus is mean state. So you have a mean state which is above 0, you have a damping.
Oh, okay.
Right?
Okay.
So yeah, if this is small enough.
Yeah, of course, because it's a multiplicative noise in nature, so you cannot cross zero. So firstly, I was just the constants there.
So actually, you can see this multiplicative noise. It will always be 0 near the boundary. Of course, here the lowest point is not 0, but there's the lowest point. You can never cross it, because once you approach this point, your noise coefficient becomes 0. So similarly here, this lower bound is 0 in this case.
I see. Thank you. Yeah, of course, the square root type of multiplicative noise as used in many other places as well.
Yeah, you're familiar with this for sure.
No. So usually people would have some stochastic version of the maximum principle used to ensure. Okay, but I see it. Thank you.
Yeah, thank you. Okay.
Very nice. Thank you. Yeah, anybody else? Any other questions for Nan? I cannot see any raised hands. Maybe I can ask a quick question. Maybe I really like I think one of the last slides. So where you described the process of going from like the PD, the deterministic PD, to the ROM.
Yeah.
Then this one. Yeah. I think this is excellent. So. And the question I had, and I completely agree with you that a lot of thinking is needed there. So this is a good point. So, but this is an interesting type of philosophical point, if I understand correctly. So what you're saying is that you take the complex system, you try to reduce it to a deterministic ROM, then you do the stochastic modeling at the ROM level, and then you leverage that, you bootstrap that reasoning to go to the stochastic to get a stochastic PD. So if I understand correctly, right, trying to bypass the ROM, so just go from complex PD to the stochastic PD, is you're saying that maybe the idea would be it would be easier, and you can run different scenarios with the ROM, see what is okay. I see. This is very interesting. This is not a usual thing. Okay.
Yeah, that's why I thought, even though I was kind of running out of time, I still think I need for two pages discussing this idea. I think there's really something, like our community of ROM can help those climate modeling, So that's why I think it's good to mention this. Yeah.
Yes, and this goes along the lines of like, so what, ROMs for engineering, this is pretty much what most of us are doing. So like you try to do things faster, but this is a little bit different. So you're trying to leverage ROMs to understand something about at the PD level. So that's very nice. Very good.
So
Thank
like this example, not just me, but this entire climate community, we always thought about building stochastic models, because we know deterministic models are terrible. It is really terrible. It's not bad, it's terrible. But for like 10, 15 years, no one knows how to build this stochastic version. Then when they are suddenly, I just, let's just try some deterministic ROM first. Let's understand what happens. Then we try to, with this low dimension system, it's easy to tune, easy to understand what's going on. Then we go back to the PD, SPD. So
it's very nice. Very nice. I completely agree. That's a nice idea, nice philosophy.
Yeah, philosophy.
Okay. So anybody else, any other questions for Nan?
Oh, yeah.
Valentin, yeah, go ahead.
I have another question, if I may. So, as I understand, and perhaps I'm wrong, many of your models use some noise which are different for the different components of your system. So, like in Fourier space, it will correspond to homogeneity in space or something like this. And is this structure can prevent you to have the right triads between the modes, the transfer of energy? Do you understand?
Very good point. This is a very good point. So let me go back to let me see what it is. Yeah. So actually, like here, what we do is we try to let me see what the equation is. Yeah, here actually. So we try to match the statistics of the stochastic equation with the statistics of the deterministic equation. And the statistics, mostly, the most important statistic is the variance, which is the energy. So we want to make sure the energy, like the U hat square, the absolute value square, the energy, in this equation is the same as this equation. So that's a necessary condition to say your stochastic model is useful. Otherwise, your long-term forecast will be wrong. It will underestimate or overestimate your energy. So actually, you can see from these two time series, I mean, just by eye, they have similar amplitudes, which means, roughly speaking, they have a similar energy. So if we plot this Paul spectrum using the stochastic model, of course, we can only plot here because we translate here, but it will almost perfectly match this time series. I mean this curve, because we did by design, we make the stochastic model to capture the spectrum. So you are definitely right, and that's one of the most important, if not most important point when we try to build stochastic models.
Okay, thank you.
Thank you. Yeah.
Very nice. Anybody else? Any other questions for Nan? No? If there are no other questions, I would like to thank Nan again. I mean, this has been an excellent talk. Thank you, Nan.
Thank you.
I really
Thank you very
appreciate
much.
it. This is exactly
you.
what we're looking for. So thank you. And
Thank you.
for this Halloween to remember, and and we'll see everyone next week for the next talk in the Nagram seminar. See everyone. Have a nice Halloween and happy Halloween. And thanks, Nan, again. Thank you.
Thank you, Tran. Thank you. It's very nice. Yeah.